So along with the idea of georeferencing images, we know now what georeferencing is and the goal of it. There are a lot of different ways of doing different methodologies. If we continue on that idea of the FW tools and the command line, the open source command line utilities, if you were to just look over a list of things that you can download, you start looking at good, powerful words like warp and build and convert and rasterize and transform and compute and you know all kinds of different things that you can do to images. Up to now, as we talked about stereo imagery and making those measurements, remember that was the whole goal of that geometry section, was to get to the stereo section and understand what's actually going on in the stereo section. The point was that every photo had distortions, and we needed to recognize and understand and measure them. From here, beyond georeferencing, we're going to go to rectification. Rectification is the process of removing those distortions. There's a lot of different methods, and they have different precisions, and they have different accuracies. But realistically, sometimes rectification isn't done at all. Sometimes the client just simply wants a pretty picture, something that's going to go for a display or hang on the wall, or just plotted and scanned and plotted, not even georeferenced. But if we are going to start rectifying in some manner, let's again step back in history a little bit and talk about in essence the analog era in photographic rectification, in these optical mechanical instruments. And in this case, the most common distortions in aerial photography are related to the image itself, the tip and tilt. And if it's tipped and tilted in multiple directions or off scale, too high, too low, those distortions just continue to add up and continue to manifest in each other. You could, because the camera was what was twisted in space, you could twist the projector in the enlarger. But since the photo, in essence, the photo has to fall on the easel, that's where the photo paper is going to go. It has to fall on the easel, so it's easier to just move the easel. So you can see in these old optical mechanical plotters, and they are old. All you're trying to do is recreate the distortions that forced those light rays to, the light ray in one corner to travel farther than the light ray in the other corner because the camera was tilted. There are not very many. I don't even know of one of these optical mechanical rectifiers anymore. For that matter, there really aren't that many photo labs left because so many things are being done digitally. But in these cases, they plot the control on that board, make the measurements, make the distortions, and what comes out is a print that is much more accurate than the original print, because at least the tip and tilt have been taken into account. Well, after that, the one of the simplest things that we can do digitally, whether it's digital or an enlargement, if we're not going to go to the tip and tilt stage, one of the easiest things that we can do is scaling. We take a point and the how many feet on the ground between two road intersections. So in this case we've got a map. We know the map is 1 inch equals 2,000 feet. We can measure based on the map scale that distance. We know that the image has a certain distance, whether we are talking about inches or we're talking about pixels. If we get into pixels, then we have to start thinking about desired resolutions. So let's say, for example, that that distance is 2,500 feet. It measures 380 pixels, so that's going to give us each pixel equals 0.658 feet per pixel. If we want the pixels to be 2 feet, all right, we're gonna have to come up with a scale factor. So we divide that and find out that one is 0.329 of the other, and if the image is 4,580 pixels wide, then for the pixels to be larger, to represent a larger area, the size of the image has to be smaller. So we take that 4,580, multiply it by the scale factor, the 0.329, and what we'd find out is if we resample that pixel or that image so that it is 1506 pixels wide, then every one of those pixels must be 2 feet. Now, of course, this is approximate, and we haven't done any tip and tilt corrections. But if all we're doing is looking for a rough scale so that we know we would be able to, how far are these other roads apart? It's not going to be exact, but it is going to give you a scale that you could actually work with and make some rough measurements. After we get into scaling, the next best thing that we might be able to do, and here we're sticking with the idea of doing it digitally. This is kind of the idea of the rectification. We're taking it the next step besides just scaling it. This is going to go back to some sort of a coordinate transformation. The scale factor was just multiplying and dividing numbers to find out how many pixels it would take to fill a certain amount of area. If the right number of pixels fills the right area, then you have the right size. It may not actually match anything, but you could make distance determinations from that. We're still in this multi-point, not changing the actual geometric shape of the image, but we're going to transform it to yield a rotation and a scale factor that could either be applied by world file, and I say applied by world file in theory because you have to have a software that recognizes world file rotation. But if you do, you would determine the rotation, and you can actually scale and rotate the image and then just drop it in behind a map. And when we're dealing with the coordinate transformation, okay, there's one way to do it where we just actually computed the scale, we computed the rotation. If we're doing a multi-point or using the matrix method, especially for least squares, for multiple points, notice that the output of that transformation was a scale cosine factor, a scale sine factor, and then of course the transformation in x and y. By taking those factors, okay, and this is if we're using that matrix method for determining the a least squares coordinate transformation. Okay. Once you do that, it's going to output some numbers. It's going to output the scale cosine, scale sine. Sine is just opposite over hypotenuse. Cosine, we know, is adjacent over hypotenuse. So if we have that scale sine over scale cosine, it's all going to reduce, and we're going to have opposite over adjacent. So if we were to take those two factors, divide one by the other, and then get opposite over adjacent, that is going to be the tangent of the rotation. So what we can actually do is take the sine, the scale sine, divide it by scale cosine, understanding that everything is going to reduce out, take the inverse tangent of that, and we will have the rotation. So the rotation factor can be derived after we've done all those other computations. Well, if we have the rotation, then we can pull the scale factor out. Okay. If the scale times the sine is a certain value, and we divide that by the sine, the sines, S-I-N, cancel out, and we're left with the scale factor. So what we're going to end up with is, if we can still use that that matrix method of coordinate transformation and do those computations, and end up with the rotation and the scale. Once we have done that, once we know a rotation factor, if we don't have a software that's able to handle the rotation of the world file, well, what we could do is we could just rotate it manually. The next method of processing we're going to call semi-rectified. Okay, in semi-rectified, it almost goes back to the optical mechanical way of doing things, where all we're doing is taking out the applying the rotations. And you remember how if you were to we take a projector and tip it, one side of the image is going to get bigger, one side is going to get smaller. Well, the same thing would apply to the photos. The semi-rectified is actually something that approaches orthorectification, and we're going to get into orthorectification next. It's just that we're not using any kind of a surface. What we're going to do is we're going to compute the rotation factors in omega, phi, and kappa. We're going to run those through a software that'll apply those things, and then output an image that hasn't been corrected for any ground shape, but has been corrected for all the other rotations. This is just about as close as we're going to get to a good measurable product without going through a full digital orthorectification process. And this really, all these slides show is that because the tendencies, the distortions, kind of add to each other, we can take something that's completely square, the number of pixels in each side of the unrectified image are the same. And once we rectify that, the lower edge has a certain rotation. The upper edge, which you can see, it isn't just a pure swing around the kappa, around the z-axis. It's actually been warped because these two, which used to be parallel, not only are they not parallel, but they're not even the same size. The bottom of the image has been stretched less than the top of the image. And then you can also look at those correspondingly to the left and right. So these are the really basic, almost manual methods of rectifying, digitally rectifying images, so that if then we were to go and try to place them behind a map, you would see that they start to match much closer. Just scaling and rotating, simply, and we will do this. We're going to take an image, actually a series of images, and physically scale them and manually rotate them and then drag them to the proper position, or actually transform the coordinates to the proper position in a map. And you'll see how well those things fit just having those manual methods